Hi, welcome to this video. Today we're going to be talking about HYSYS. Specifically, we want to talk about how to build a methanol plant from scratch in HYSYS. So this was based on the final year project I was embarking on previously, and well, we've made a lot of mistakes and got a lot of experiences. So I want to share them with you guys. Some of the tips and tricks we've learned in HYSYS, and hopefully it's helpful to you in your simulation, or if you're doing a similar design project, it will be the same. So yeah, we're gonna start first with the component properties and fluid packages, of course. And just to reiterate, our problem is going to be about capturing some flue gas, which is full of impurities, and producing methanol from it. So that will probably have to take place through a catalytic reactor, and we'll probably be using some amines in order to get rid of our carbon dioxide. No, capture our carbon dioxide from our flue gas and purify that and go into to make methanol. So first thing first, we'll probably have to start adding some of the components. So as you can see here, we are going to add lots of components. So first thing first, since we are making methanol, right, we'll have to be adding methanol. You have to add water, and then we'll have to add lots of other stuff as well. So as you can see, I'm typing to get methanol. So I'm clicking on methanol. You can just click the add button. Yep, so methanol has been added, and I'm going to add water as well. I'm just going to press enter. So I'm going to speed things up a little bit. Yeah, I'm going to add carbon dioxide. I'm going to add carbon monoxide. Yeah, I'm going to try to add carbon monoxide. Yeah, so okay, this doesn't seem to work. All right, so yeah, carbon monoxide first. You'll see whether it's a bit hard to find. Then I'll just press the add button. Oh, yeah, that seems to work. Okay, so besides that, you'll probably have lots of other stuff too, like probably like hydrogen, I think. Yep, so we're gonna add hydrogen in, and on top of that, we'll probably have amines. So I'm gonna add DE amine now, the diethanol amine, monoethanol amines, and methyl diethanol amine, or MDEA. And these are some of the amines we want to compare to see how efficiently each of these amines can absorb CO2. So these are just some of them. And one more amine which is less known is called diisopropanol amine, or DIPA for short, DIPA. So I'm just going to check whether it's the correct DIPA. So I'm looking at the CAS number, which is 110-97-4, 110-97-4. And I'm going to search online to see whether it's the correct DIPA that we are talking about. So if you're not sure whether the component is correct, you can go and check the CAS number online. And there we go. Sigma Eldritch is the first one. So yeah, diisopropanol amine. So click on that, and basically we'll see it's the correct structural formula. It's exactly what I want. So this is diisopropanol amine, which is one of the amines used for acid gas capture, such as CO2, SO2, H2S, etc. Get some water. Yeah, so DIPA. Yeah, so we'll probably be looking at DIPA. And on top of that, we'll probably have to add some of the actual acid gases that we are capturing as well. So I'm just going to add a bunch of other acid gases commonly found in flue gas. For example, besides CO2 and CO, you'll probably have the usual oxygen and nitrogen. And of course, actually, yeah, now I want to try the triethanol amine. So I'm just going to put in the whole suite of amines into my component list first. Yeah, so yeah, whole suite of amines in the component list. So MEA, DEA, TA, MDEA, and DIPA. So we have methanol, H2O, CO2, and all the amines that you see here. And yeah, so what was I saying? Yeah, you'll probably have some other gases in the flue gas as well. hydrogen sulfide and SO2. Though hydrogen sulfide will be less common. And of course you have oxygen and nitrogen dioxide. Oh, caffeine. No, you definitely don't have caffeine in flue gas. Okay, so nitrogen dioxide, other oxides of nitrogen. So I'm trying to find NO, or nitric oxide. Not successful, and that simulation name no, that doesn't seem to work. So let's try finding some ways of getting the thing to work. Yeah. Let's see. Yes, nitrous oxide. Okay, that's one of them. Probably you might find it in flue gas. So let's see whether you have nitric oxide. Okay, that's what I was looking for. Yep. So these are some of the common gases you can find in flue gas, just to make it a real thing. So we have SO2, H2S, and now we want to look for SO3 as well, because you can find that in flue gas. And SO3 and H2O, that gives you sulfuric acid. And these are the kind of things you have to consider when you are doing a flue gas capture system. Okay, so I'm just going to rename my component list as my component list. Now, what you may be asking, why we want to do such a thing? Well, of course, I like to do it to keep the fluid packages and the component list neat and tidy, so I know that if I'm referring to this component list, it will be quite orderly in a sense, because probably in the HYSYS simulation you're going to have lots of fluid packages, such as acid gas. So I'm going to add acid gas now. So you have acid gas, lightning, thunder, I mean. Yeah. Anyway, acid gas, yes, it will capture some of the CO2, SO2, etc., etc. So yeah, acid gas and Ping Robinson, or even the ASME steam tables. So you're going to have multiple fluid packages, and you don't want to have them named as basis 1, basis 2, etc., etc. So instead of that, I'm going to just rename everything, and going to rename everything as what it should be. So if I'm going to select acid gas for this, I'm going to name the basis as acid gas. Yep. So that's what I'm going to do. I'm going to rename. I'm just going to put it as acid gas. So acid gas. I'm going to press the OK button. And yeah, you want to look at other fluid packages as well. So the other thing I want to look at is the extended NRTL package. Yeah, the NRTL package, which stands for non-random two-liquid model. This is a very important thermodynamic model. And for the gas, I'm going to the vapor model, I'm going to use Ping Robinson. So NRTL actually talks about what do you call that? Yeah, it talks about the fugacities. It helps you calculate the fugacities of the fugacity coefficient of the liquids. So yeah, I'm going to add it as a separate fluid package. So just besides acid gas, I'm going to have NRTL as well. Though acid gas is pretty good, actually it's very accurate in predicting methanol distillation at around atmospheric pressure. I'm not showing it in this video, but some other videos I can show that. But anyway, yeah, I'm going to add, I'm going to put the extended NRTL is basis under this basis 1, but I'm going to rename it as the extended NRTL dash Ping Robinson, because I want to be orderly. I'm going to look at some of the other things in this property package, but first before that, let's rename it as the Ping Robinson extended NRTL package. So it's just for orderliness, yeah, like I was emphasizing before. You should be very orderly. Should be very orderly when you do your HYSYS, so that you don't spend time, you don't waste time on unnecessary things. So you have extended NRTL, and one more I want to add is the steam table. Now, what's the steam table used for, you may ask? The steam table is used for water, specifically water. So as its name suggests, it's all the thermodynamic data of water. experimentally found. So I have to attach it to a component list that contains only water. As you can see now, it's saying that components are incompatible with the property package. So that HYSYS has made an extra component list known as component list 1 in this video that contains only water. So the ASME steam tables can only be paired to water because it only has data for water. I mean, obviously. So yeah, I'm going to rename this component list as water only because it only has water as compared to all the other components in this my component list. So the ASME steam tables are here. So yeah, I want to rename it this basis 1 and the component list 1 as the ASME steam tables respectively. And I want to change component list 1 into water only. So yeah, water only. Yep. So that's pretty much it. We have made the ASME steam tables. The component list is only attached to water. As you can see on the screen here, it's quite clear which fluid packages are attached to which components. So yeah, pretty much that's it. So the ASME steam tables are here as follows, and the Peng-Robinson extended NRTL package. So extended NRTL again. Oh yeah, one thing I almost forgot. You might want to estimate the binary coefficients. So what's the binary coefficients do? Binary coefficients actually help us to calculate the fugacity coefficients of the liquid. Okay, so it's very important for the VLE data. So you can just press all binaries on the right, then you'll just estimate all the binary coefficients for you, and that helps you to get out all these numbers out, so that hopefully it's regressed with experimental data. And yeah, that's basically what you need before you start simulating whatever things you got in HYSYS. And we are almost at the end of this video, so in the next videos you'll probably want to start setting up the reactors and the reaction packages, etc. So do stay tuned for the next video. Yep, and probably the other tabs you can just ignore for now, if not there's too much to explain or try and explore for that matter. So I'll probably see you in the next video. Thanks for watching, guys. Bye.